Good morning, students. Day 15 we have today of our crash course, and we are studying waves and sound. We are starting waves and sound now. Okay. So waves means is a disturbance, you can say, in a medium created which carries energy and momentum with it. Okay, a source is there which creates a disturbance, and with the property of that medium, okay, that energy is carried forward. That is what we are calling as wave. Okay. So a disturbance that carry energy and momentum. That carry energy and momentum. We are calling it as wave. So do we require medium for that? No, we are understanding with the help of the medium. But there are certain waves in which medium is not required. Right. So there are two types of waves. There are two types of waves. Mechanical and non-mechanical. Mechanical wave and non-mechanical wave. Non-mechanical wave. Non-mechanical. Okay. Mechanical wave which requires medium for propagation. Which require medium for propagation. Okay, non-mechanical, which does not require medium for propagation. It does not require medium for propagation. Okay. Now, mechanical wave, first we will see non-mechanical wave. Non-mechanical waves are also two types of waves or two waves that we study. What are those? Its examples. Example number one is electromagnetic wave, which we have a separate chapter. Okay. And second one is matter wave. That also we have as a topic. Okay. Electromagnetic wave and matter wave. Both comes under non-mechanical wave. So electromagnetic wave is which is carrying electric and magnetic field, in which electric and magnetic field both are perpendicular to each other. Right. And what is matter wave? When matter moves, carry certain momentum. Okay. Then it produces a wavelength or a wave that we are calling as matter wave. Like electron is there, electron is moving with certain speed. Okay. So there is wave nature associated with that. Right. De Broglie proved it. Right. So that is matter wave. Mechanical wave. Now mechanical wave also we study it as longitudinal wave and transverse wave. But before that, EMW is what kind of wave? This is transverse. This is also transverse. And matter wave, transverse. Okay, what is transverse and longitudinal we are going to see. Now, mechanical wave. So, mechanical wave also can be two types, transverse and longitudinal. Okay, this is two types here, transverse and longitudinal. Transverse and longitudinal. Okay. Now, question is, what is transverse? Okay. What is transverse wave? Then we have to go in the end. Okay. here we are. Okay, so transverse wave. Transverse wave is what? Transverse wave means when medium particles are oscillating perpendicular to the propagation of wave. Okay. When medium particles are propagating perpendicular to the propagation of wave. Okay, it moves in the form of crust and trough. It moves in the form of crust and trough. Okay, it moves in the form of crust and trough. And how will be the shape? Okay, make the shape of the wave. The shape of the wave is like this. Moves in this form. Okay, this is crust here and this is trough. Sometimes it is referred as mountain and valley. This is mountain and this is valley. Okay, so mountain and valley. It moves in the form of crust and trough. This is transverse wave. And its example is, the best example is waves in string. Waves in string. Okay, this we can view and visualize it how it's moving. If you are going to produce a disturbance like this, hold the string in your hand and make the motion like this. So how is your motion? Perpendicular to the length of the string. String is like this and you are making it in this way. Okay, so your hand is moving perpendicular whereas energy will be moving forward. That is waves in string, which shows us transverse wave. Okay, then we have longitudinal wave. Now what's longitudinal wave then? Longitudinal wave. Okay, so in longitudinal wave, medium particles move along the direction of propagation of wave. A wave in which medium particles move along the direction of propagation of wave, along the direction of propagation of wave. Okay, they move in the form of compression and rarefaction. These waves move in the form of compression and rarefaction. Okay, compression and rarefaction means what? You can call it as expansion. Okay, what happens in gas? Compression and expansion. So compression and expansion we can call. Okay, so compression and rarefaction. Fine. Then how to show them? There are two ways to show them. One, through the displacement. Through the displacement we can show compression and rarefaction. Whereas in another way we show them in the form of pressure wave. Okay, and that we will show in the form of crust and trough only. Okay, so both are the forms in which longitudinal wave can be shown. So first is how we can show them in compression and rarefaction form in displacement wave. So at one place you will have slightly relaxed particles are like this. Okay, in this way. Then suddenly there will be suddenly there will be compression. They will be very close to each other here. Okay, something like this. Then again, rarefaction. Okay, one more time we'll make compression also. I hope it's visible to you. Like this it is. Okay, so one here is compression. Sorry, one is rarefaction. This is rarefaction. This is compression. This is rarefaction again. And this is compression. Okay, so rarefaction, compression, rarefaction, compression. Like this, it moves. Okay, this is how longitudinal wave is shown in displacement wave. But if suppose you want to show in terms of pressure, then it's very similar to our transverse wave. Okay, so first is rarefaction we have shown. So it'll be like this. Like this it will go. So this is rarefaction here. This is compression. This is rarefaction. Okay, and what is this? Pressure. This is pressure here. This is pressure. So here pressure goes down, that means rarefaction. Pressure goes up, compression. Again pressure goes down, rarefaction. So this is how we will be showing longitudinal wave. Okay, then what? If we go back to transverse wave, this is transverse wave. And this here, from here to here, we call it as one wavelength. This is a wavelength. And what is a wavelength? Which we represent with lambda. Lambda means a distance traveled by the wave in one time period. Whose time period? Particles which are oscillating in this one. Okay. First thing is waves means is in this one particles are doing oscillation. Okay. Both types. Whatever type of wave we are talking, in that one particles are doing oscillation. Okay. So wavelength is what? Distance traveled by the wave in one time period. So I'll write it over here, wavelength, or we'll write here wavelength. Wavelength lambda. So distance traveled by particle in one time period. Particle in one time period. One time period of oscillation. One time period of oscillation of particles. So all the particles are doing oscillation of same time period? Yes. Same time period as source. The source means if suppose the hand which was producing the disturbance, if its time period is t, then time period of fall is t only. So lambda basically is distance traveled by time. Sorry, I have written it wrong. Velocity of wave actually is distance traveled by time. Okay, and if this time is time period, then this d is actually wavelength. Okay, this is lambda by t, and I should write this as small t actually. Okay, distance traveled by time, which is equal to lambda by t. So v is equal to lambda by t, and 1 by t can also be written as frequency. So this is lambda into frequency. So velocity is equal to wavelength into frequency. This is most common formula associated with waves. Okay, so that's lambda. Now let's come back again on waves. When we are saying that in this one particle is doing oscillation, the particle is doing oscillation, it means this particle will go forward and then it has to come back also. Right. So then what property is required for it to do all this? Elasticity, because it has to regain its shape. Okay. Suppose if I say that I am producing a wave in spring, a spring. Spring, which kind of wave can be produced? Longitudinal. Okay, so longitudinal wave we are producing in spring. And what happens in spring? We all know that it will be expanded, then we compress, expanded, compression. So what is the property it has? Elasticity. Okay, so for wave, it's necessary in a medium. For a wave, it's necessary that medium must possess elasticity. Must possess elasticity. Must possess elasticity. Possess spelling is what? I don't know why I'm getting problem in that. Possess double S, E double S. Is it correct? Students?
Yes, sir.
Okay, double S, right? Okay.
Yes.
For a wave, it's necessary that medium must possess elastic property. Okay, so it means is other than elastic property, any other property also required in a medium? Yes, that is required, but elastic property is very important. So, first we'll write for a wave, in a medium. Now, okay, fine. Elastic property is required so that the particle can do SHM. Fine. But at the same time, we have to move the energy also. Energy has to move ahead. Okay. And the particle in this one are in motion. So, what energy they will have? Kinetic energy and potential energy. And if suppose kinetic energy we require, that means they must possess mass also. Mass means is inertial property. Okay. So, first is they require elastic property, true. But at the same time, they require inertial property also. So, I am directly writing in this itself. Okay. So, for a wave, it's necessary that medium must possess elastic property and inertial property. Inertial property means mass and inertial property. Okay. For a wave, it's necessary that medium must possess elastic property and inertial property. Fine. Understandable. Then, elastic property, then we are saying that which type of elasticity is required. Because three types of elastic modulus we have seen. Young's modulus is there, bulk modulus is there, shear modulus is there. Which one is required? Okay. So now we have to see, if you talk about transverse wave, okay, transverse wave in string, transverse wave in string. Okay, now which type of wave it is? Transverse means is in which particles are moving perpendicular to the propagation of wave. Okay, so in this one, which type of elasticity we require? Okay, which type? See, Young's modulus also do. Transverse wave in string or rod also you can write, both the same thing. Okay, so here we say Young's modulus. Okay, why Young's modulus? Why elastic property? That I told you through SHM. But at the same time, one more thing is there. When you are making this wave in any medium, and we said that it is creating disturbance, changes are being made. Particularly longitudinal wave, there is a compression and rarefaction. That means change in volumes are happening. And change in volumes are happening in longitudinal means I am directly giving you the reference that bulk modulus is involved. Okay. So when we say longitudinal, okay, in liquids and gases, liquid and gases, then what is required? Bulk modulus. But is it possible to produce longitudinal waves in solid also? Yes, why not? You can produce them in solids, then shear modulus is involved. Okay, so this is how all the three modulus of elasticity are involved in waves. Transverse wave, Young's modulus; longitudinal wave, liquids and gases, that is in fluids, bulk modulus; in solids, shear modulus. Okay, right, let's move back then. Let's move back long, okay, to initial slides where we are. Here we were, okay, when we're talking about waves, right? Let's move ahead. So now next is what? After studying about waves, type of waves and all that, the initial information, equation of a wave. Now equation of a wave is shown to you something like A sine kx plus omega t, or y equal to A sine kx minus omega t, or y equal to A sine omega t minus kx. Like this it is shown to you. Okay. Right. So this is how it is. How it came, we are not going into that right now. Okay. So what this is in this one? A represents amplitude. A is amplitude, and what is amplitude? The maximum displacement of the particle from its mean position. Maximum displacement of particle from mean position. It means if I am going to make a transverse wave here. Okay, this is the transverse wave. Then this is called amplitude. This is the maximum displacement a particle can have from mean position. This is amplitude. Okay, K is called propagation constant. It depends on medium. This is propagation constant. It depends on medium, and this K value is equal to 2 pi by lambda. Lambda is wavelength, we all know that. K is equal to 2 pi by lambda. Okay, then omega is related to the particle which is doing oscillation. Okay, and omega is equal to what? 2 pi by t, where t is time period of oscillation. Then we have velocity of wave in this one. So velocity of wave is what? Velocity of wave is omega by k. Omega by k, or frequency into wavelength. That is also fine. Okay, because k is going to give us lambda, and from omega we will be getting frequency. Okay, so velocity of wave is omega by k. Now there is basic difference between these all waves, okay, that I have shown. Now what is this? This is saying us that its direction is towards negative x-axis, whereas these two are moving towards positive x-axis. Okay, the first one, this one, or I'll make it with a different color. Okay, that's green. So green one. Okay, wave is moving towards negative x-axis. Okay, whereas the remaining two, these remaining, okay, waves are moving towards positive x-axis. Waves are moving towards positive x-axis. Okay, so these two are moving towards positive x-axis, this is moving towards negative x-axis. And what is the difference between the two? The difference between the two is the first one we can make like this one. Okay, the first one is like this, and the second one And the second one is like this. Okay. That is difference between sine kx minus omega t and sine omega t minus x, nothing else. This is also going towards positive x-axis, this is also going towards positive x-axis. This starts from trough, rather this starts from crest, whereas this starts from trough. Similar waves. That means at first your hand goes up and the second one your hand goes down first. Okay, that is the meaning of this. So this is how we are going to show the equation of waves. Okay, wavelength I have already told you. Velocity of wave is omega by k in this one. Then velocity of particle. Now if this is showing us wave equation, in this one y is what? Y means along y-axis. So who is moving along y-axis? Particle. Particle is only moving up and down. Wave is moving along x-axis. So if this is showing displacement of particle, then velocity of particle will be dy by dt. Velocity of particle will be dy by dt. Okay, so what that is going to come? Velocity of particle. Okay, that is dy by dt. So if you are going to differentiate this, suppose this one we are differentiating. So dy by dt of velocity of particle is going to come as a omega or minus a omega, you can say, minus a omega cos kx minus omega t. Okay, minus omega because here minus omega t is there. So it is minus a omega cos kx minus omega t. That is the velocity of particle. Now, which particle's velocity is this? Because this is a function of x as well as t. Okay, so this gives velocity of all the particles which are there. Whichever particle you want, just put the x value and time value. That will give you velocity of that particle at that instant. So that means this wave equation represents all the particles, okay, at the same time. That's why x is also there and t is also there. So this is velocity of the particle. What is the maximum velocity of particle in this one? Maximum velocity of the particle will come a omega. Okay, maximum velocity of particle, V max of particle, we can write plus minus a omega. Okay, other than this, any general equation is there? Yes, we saw in SHM. Okay, velocity of particle. What we saw in SHM? Omega root over a square minus y square. Definitely that is also there. Okay, because particle is doing SHM only. So omega, the velocity of particle is omega into root over a square minus y square. That is also valid over here. Okay, so this is related to equation of wave, wavelength, time period, frequency, velocity of particle. Okay. Then what we have? Ratio of wave velocity and particle velocity. Okay, fine. Acceleration also we can talk about for the particle. Okay, it will be same as in SHM we saw. Maximum acceleration will be omega square a, right? So ratio of wave velocity and particle velocity. Fine. So what is wave velocity first? Wave velocity is omega by k. Okay, and omega basically is what in this one? Remember that it's not necessary that the equation will be given in terms of k and omega. They can write you, they can give you a question. Suppose the question is like this. Question is given to you. That equation is there, which is given in the form of p sine ax plus bt. And they ask you what is velocity of wave. Then what you will do? Here omega is actually, omega means is coefficient of t. Okay, what is along with t here? So b, say b. And k means what is the coefficient of x? So here velocity of wave will become plus v by a. Remember that. Or 3x plus 4t, 5x plus 2t, 6x plus 9t. Okay, Like this it will be written, so you should be able to find out velocity of wave. Okay, fine. So velocity of wave is what? Omega by k. Now velocity of particle. Now velocity of particle, if we have to write and we have to find this ratio, then we need to know that whether he is talking about maximum velocity of particle or what. Okay, if he is talking about maximum velocity, then that is a omega. Okay, so then we want the ratio. What's going to come? Omega by k to a omega. Omega gets cancelled. Okay, what we are getting? 1 by ka. Right? Correctly I have done? Yes or no? 1 by Ka. This is the ratio of the velocities. Okay, but if it's not maximum, then it will be in terms of T. Whereas this is constant, here this will become in terms of T. Okay, so velocity of wave is this only. Velocity of particle, if you have tried, what you will be writing? You will be writing like A omega cos kx minus omega t. So in this one, time factor is there. Okay, so definitely this is ratio of wave velocity and particle velocity. What? Which particle velocity? Maximum particle velocity. Okay, all right. Then you have a question. What is the question now? Y equal to a cos 240 t minus x by 12. What is phase difference between 2 points 0.5 meter apart? I am asking phase difference. Okay. So before going to this question, let's go back to the wave equation. Okay. Now in this one, y equal to a sine kx plus omega t is there. Now what is the phase of a wave? This entirely is called phase of a wave. Okay. Kx plus omega t, and if suppose some phi is also there, something like kx plus omega t plus phi, then this entirely is called phase. And what is phi then? Phi is called initial phase. Okay, so this is phase. So if I have to find the phase difference between the two waves, okay, between two waves first. So if you have to find between two waves, what do you do? I'll just show you that. Okay, so two waves I am writing first. Y1 equal to A1 sine. Now suppose that an entire thing that was there, I am writing this is phi 1. What is this? Kx minus omega t plus phi, or kx plus omega t plus something. Okay, and y2 is equal to something like a2 sine phi 2. So then phase difference, when I am saying, what is that? That is actually phi 2 minus phi 1. That is called the phase difference between two waves. But here they have shown you only single wave to us. Okay, in that single wave itself, he is asking phase difference between 2 points, and both those points are doing SHM only. Okay, so both the points are doing SHM. Now how to find phase difference between the two? Okay, so we all know that even the particles which are doing SHM, they also have phase. Okay, now what we used to write? Y1 equal to A sine omega t plus phi. This is for SHM. This is initial phase. Okay, the same way Y2 equal to A sine omega t plus maybe something else, right? It's like this. So two particles are there at the same time. Time is same, but their phases are different. Here is saying what is phase difference between 2 points 0.5 meter apart. They are at a separation of 0.5 meter because they are representing a wave. They are not representing just a single particle which is doing SHM. Okay, so it's representing wave. So in this one, what is the difference between this and a particles doing SHM in waves? Then there is position of the particle. Position is the difference. Okay, like if I am writing wave equation A sine kx minus omega t. Okay, So for two particles, when I am showing it, I will be showing it like this. Will they have same amplitude? In a wave, when the particles are there, all the particles are doing SHM, are they having same amplitude? Yes, they have the same amplitude. Then what is different? Their positions at different time is different, okay, and their x is different, their position is different, okay, and they may be at different position in doing SHM also. What does that mean? It means is, if suppose this is how a wave is, okay, and I have taken one particle is here, this is my first particle, where it is at this position, and second particle I have taken here, where it is at this position. So not only their x coordinate is different, but their y coordinate is also different, because at different time they are at different positions. Okay. So here I showed you all this. So what is the phase difference? Suppose y1 I am writing. So y1 I am writing as a sine kx1 minus omega t. Time is same, remember. Y2 is again a sine kx2 minus omega t. So when I am going to find phase difference, that means this minus this, what I am going to get? Phase difference is k x2 minus x1, that is k delta x. Okay, between two waves also it will be coming same way, k delta x only. Okay, now here is also k delta x. So what is k value? First let's find out what is k. K means 2 pi by lambda. What we have? K only we have. Yes, we have k. K means is coefficient of x. So 240 into x by 12. Okay, so 240 by 12, that is 20. This is the value of k. Okay, so put it here 20. Now delta x value is given 0.5. So 0.5. So answer is 10. Okay, so phase difference between 2 points 0.5 meter apart is 10. That's correct only, no? K delta x, right? So 10, right? 10 radian. This is how you can find phase difference between two points. Okay, let's see for further what it is. Okay, wave velocity, velocity of wave in string. Okay, fine. So we already have seen that omega by k is the velocity. Now something else we are going to study then. So what it is? As we said, when wave is moving in a medium, it requires two properties. What are those? Elastic property and inertial property. Elastic property and inertial property. Okay, so velocity of wave, here is what? String. So velocity of wave, in fact velocity of wave in general also. Velocity of wave actually is root over elastic property by inertial property. Okay, general velocity of wave is equal to root over elastic property by inertial property. Now the question is, when we are talking about a wave in string, what represents elastic property? Now elastic property normally is represented by modulus of elasticity. In string, we said Young's modulus is there. Okay, but here we are going to represent it in the form of tension. Okay, tension, and by inertial property is linear mass density. It is density only, but linear mass density. Okay, so here is tension. Tension means is, you can say stress. Stress is given by tension only in the string. Okay, so when we talk about string, it becomes root over T by mu. But when it becomes in rod, same velocity of wave, we will be talking as Young's modulus of elasticity by density of the rod. What is y? Young's modulus. In fluids velocity of wave will become, in fluids which modulus of elasticity? Beta. Beta means bulk modulus. So then formula becomes root over beta by rho. Okay, so in string root over T by mu, in rod y by rho, and fluid it is beta by rho. Okay. Okay. Then velocity of sound. Now velocity of sound, this is what actually longitudinal wave. You require a medium for sound to propagate. And where sound propagates? Sound can propagate through rod also, and it can propagate through liquids also and gas also. But which one we prefer? We prefer it in air. So, but still it is gas only. So, velocity of sound is also V equal to root over beta by rho. This is only the form. Now, what is beta? Beta we have studied, it was something like delta P by delta V by V. So, V is here, negative. Okay, what it is? Volumetric stress to volumetric strain. This we can write as like this also, minus dP by dV into V. Okay, this is how we can write. Then what more we can do? We can find out that any other form is there in which we can represent this. So yes, we can. Bulk modulus we can find for gas. Okay, so we can find, through which we can find another formula for velocity of sound. Okay, but at the moment V equal to root over beta by rho we are keeping in our mind. Okay, we are moving ahead. Okay, let's see a question now. It says velocity of sound is 330 meters per second and wavelength associated with that wave is 110. So frequency, very basic question is asking. So V equal to what? Frequency into wavelength we know. So this is 330, this is F, and this is 110. So frequency is 3 per second. Okay, 3 per second, very basic question. Alright. Okay, in steel wire, Young's modulus is given to you 4 into 10 to the power minus 2 and density is given to like this. What is velocity? Very simple again, direct formula based question. So V equal to root over Y by rho. So this is 4 into 10 to the power minus 2 by 10 to the power 4. Okay, so 4 into 10 to the power 6. Answer is 2 into 10 to the power 3 meter per second. Okay, next. Another question is there, but this time in liquid. Okay. What's given? Beta is given and density also given. So we know the formula. V equal to root over beta by D. 2 into 10 to the power 5 by 8 into 10 to the power 3. Okay, so 1 by 4 into 10 to the power 2. Okay, so answer is 1 by 2 into 10, 5 meter per second. Okay, 5 meter per second. So this is how we calculate velocity. Okay, fine. So now we have Newton's theory. Newton's theory related to velocity of sound. What says Newton? Newton said that when sound passes through air, okay, then temperature remains constant. Now when sound passes through air means its compression and rarefaction are happening. Compression, expansion, compression, expansion. So Newton said that the temperature is not changing in that. Okay, temperature is not changing. Passage of air or passage of sound, not air. Passage of sound through air is isothermal process. Isothermal process. Okay, So then he found velocity. We already know that V is equal to root over beta by rho. Now beta's value is what? When it is isothermal, it is equal to pressure. We have calculated that, okay? That's equal to pressure. So it will be this root over P by rho, okay? But then Laplace came. Laplace said that the process of passage of sound through air is not isothermal, okay, but it is adiabatic. He said that this compression and rarefaction are happening so fast in the nature, there is no chance for a medium, okay, to actually show the exchange. What is it? What is adiabatic? That means there is no exchange of energy between system and surrounding. Okay, so there is no exchange is happening because the process is so fast. So its temperature is not constant. Temperature is going up and down, but it is not visible. Why? Because it's very fast. Okay. So what is Laplace correction? He says that passage of air again I am writing passage of air, passage of sound through air is adiabatic process. Adiabatic process. Okay, so velocity is beta by rho and beta is actually gamma p by rho. Okay, so this one was rejected and this was accepted, and it gives value also exactly whatever value we measured for the sound experimentally, this formula also gave the same. So it's gamma p by rho, which further we all know that this rho we can write as mass by volume. So this can be written as gamma PV by mass of the gas, and PV is nRT, we all know. So finally we get gamma RT by molecular mass of the gas. Okay, this is mass of the gas, this is molecular mass of the gas. We'll write it. M is mass of gas or mass of air, whichever is involved here. Okay, and this is molecular mass. Right, so this formula is important for us. Which formula? This formula. Okay, then velocity of wave depends on what? Velocity of wave depends on temperature, we saw that. Okay, it depends on temperature. Okay, it depends on temperature over here. Then it depends on type of gas. Yes, gamma is there. Okay, then it depends on pressure. No, it doesn't depend on pressure because the pressure is increasing, volume decreases. If volume is increasing, pressure decreases. Okay, so it doesn't depend on pressure, it doesn't depend on density. Okay, it doesn't depend on pressure, it doesn't depend on density. It depends on temperature, and then it depends on type of gas, and then it depends on humidity. Humidity in the atmosphere. Okay, more the humidity, more is the speed. Okay, the speed is directly proportional to humidity. Remember that. Okay, speed is proportional to temperature, speed is proportional to gamma, speed is proportional to humidity. More the humidity, more is the speed. Right? Okay, fine. Let's go to this question then. What is it? What velocity is 332 meter per second. Velocity of sound is 332 meter per second at 300 Kelvin. Then what is velocity at 600 Kelvin? Okay, so we know that V is directly proportional to root T. So we can write V1 by V2 equal to T1 is directly proportional or inversely proportional. Inversely proportional. What happened to me? V is directly proportional to root T. Perfect. Okay. V is directly proportional to root T. Fine. So this is root T1 by T2. Okay. So V is given to 332. Here is V. That's equal to 300. Okay. By 600. So V is coming 332 root 2 meter per second. Okay. So this kind of simple questions are also asked. Yes. These kinds of simple questions are also asked. Okay. Let's move ahead. Velocity is 332 at 300 Kelvin. Okay. Temperature is constant. Alright. Pressure is doubled. What will be new velocity? Temperature T you have made constant only. Okay. Pressure you are doubling, but we already discussed that velocity of sound doesn't depend on pressure. Okay. If pressure you are changing, density also changes accordingly. So, it does not depend on pressure. That means its solution, its answer is 332 only. Velocity of sound does not depend on pressure. Does not depend on pressure. Okay. Alright. Next. Velocity of hydrogen is 1400 meter per second. Okay. Velocity in mixture of hydrogen and nitrogen having volume ratio 4:1. Alright. What we have to do here? Velocity in mixture of hydrogen and nitrogen. So any relation is there? V in mixture, what we can do? Density of mixture we know. What we can write? This is mass of mixture by volume of mixture. That we can do. Okay, so it means we have to go for which ratio, which formula, which is related with density. Okay, which formula is that? This one. Okay, that is gamma P by rho, and obviously the pressure here is not being changed. Okay, so mass of mixture to volume of mixture. Let's find out what is the density of mixture first. So mass of mixture means mass of gas 1 plus mass of gas 2. Okay. Alright. So what he says? Mass of gas 1 plus mass of gas 2. Mass means is what? Density of that one into volume. Correct only, no? Mass of gas 1 plus mass of gas 2 by volume of mixture. Now in this one, some more information is required. Okay, what is that? Densities are required that I am not given in this. Okay, the density of hydrogen, something is required. Suppose it is X, and density of nitrogen, maybe it is what 2x or 3x, something like that. Will it work for us? Yeah. Okay, normally some value will be given, so I have written it as x and 2x. Okay. So density of mixture we have written as mass of gas 1 plus mass of gas 2 by volume of mixture. So mass of gas 1 we'll write as what? Density of 1 into volume of 1 plus density of 2, volume of 2 by V1 plus V2. Right, so what is given here? Density of 1 is x, we have taken it as x, or given as x, and volume of hydrogen, he says that volume velocity in mixture of hydrogen nitrogen having volume ratio 4:2. Okay, so hydrogen is 4 volume. Okay, 4/5 of actual volume. So okay, right? So 4/5 of volume you can write, or 4 also you can write. So 4/5 of volume I am writing for hydrogen. plus nitrogen, this is 2x, and this is how much? 1/5 of the volume by total volume. So what we got? V gets cancelled. It is 4x by 5. This is 2x by 5. This will come as 6x by 5. So that is density of the mixture. Right. Now velocity we have to find. So what it is? Velocity of hydrogen. Okay, by velocity in mixture. Okay, this was gamma p by rho of hydrogen by gamma p by rho of mixture. Okay, so this comes out to be what? Rho of mixture by rho of hydrogen. Okay, so let's put it. What is density of mixture here? 6x by 5. And what is density of hydrogen? That is x. So that is root 6 by 5. Okay, now velocity, hydrogen we already know how much it is. So 1400. So velocity in mixture is 1400 into root 5 by 6. Okay, so this we solved with the help of formula root gamma p by rho. Okay, gamma p by rho, and gamma is same here. Why? Because hydrogen is also diatomic and the mixture is also diatomic. If mixture is changing, then we have to find gamma for the mixture. That we saw how to calculate in kinetic theory of gases, how to calculate CV of the mixture. If you don't remember, again we can write that. Okay, so CV of the mixture, how to calculate CV of the mixture, we will do it here. CV of mixture, N1 CV1 plus N2 CV2 by N1 plus N2. N1 and N2 are what? Number of moles. Okay, so N1 CV1 plus N2 CV2 by N1 plus N2. So accordingly they will give here. Here they have not given in that way. Okay, accordingly they will be giving us the information about moles also, and then we can calculate CV. Okay, so here because both are diatomic, so we didn't calculate gamma. Gamma gets cancelled automatically. Okay, let's move. Now what is the superposition of waves? A superposition of waves, if suppose we have two waves, which is y1 equal to a sine kx minus omega t, and another one also you take in the similar one, this is a1, and y2 is equal to a2 sine kx minus omega t. Okay, so that means first wave is like this, and second wave is like this. Same, no? Kx minus omega t, kx minus omega t. So frequency is also same, wavelength is also same, everything is same. But what is different? A1 and A2. So what happens when you are going to do superposition? Then their amplitudes here. Okay, this is A1 and this is A2. Okay, they are going to add. So resultant amplitude here will become A1 plus A2. Okay, here also A1 plus A2. But if suppose they are in opposite way, suppose I am going to show you like y1 equal to a1 sine kx minus omega t and y2 equal to a2 sine omega t minus kx. What will happen? Then we are going to subtract. Why? Because I'll show you that how it is. Okay, so one is like this. Okay, and second one is like this. Okay, so they are having opposite phase. This and this are 180-degree out of phase. They are having same phase. Both are in same phase. and here both are in opposite phase. So the question is how to find superposition. In superposition, two things are there which we normally find. What is the amplitude of resultant wave and what is the phase of resultant wave? These are the two things which are asked from us and we find also. So how to find that? Very simple. First thing is we have to find out the phase difference between the two waves. Okay. Once we know the phase difference between the two waves, we are going to consider that phase difference as angle between A1 and A2, and we are going to add them vectorially in a parallelogram. Okay. So suppose this is A1 and this is A2, and this is the phase difference between the two, any moment. Okay. So what we know about vector addition, this will be the resultant, and resultant used to be what? Root over A1 square plus A2 square plus 2 A1 A2 cos phi, and cos phi is what? Phase difference between the two. Now in this one phase difference was 0. So here amplitude will become what? Keep here A1 square plus A2 square plus 2 A1 A2 cos 0. Okay, so this actually is A1 plus A2 whole square. So here answer will come A1 plus A2. In this one, what is the case? Here they are 180 degree out of phase. So here amplitude will become A1 minus A2. But if it is something else, then we are going to put in this one. Okay, let's do one question, then you will understand. Okay, here is the question. Okay, this is like this. The two waves are there, A sin omega t minus kx, another A sin omega t minus kx plus 2 pi by 3. What is phase difference between the two? Phase difference between the two is 2 pi by 3. What is he asking? Amplitude. So amplitude is A equal to root over A1 square plus A2 square plus 2 A1 A2 cos phi. Okay, what is A1? A. A2, that's also A. It's 2 into A into A into cos 2 pi by 3. Cos 2 pi by 3 means what? 120 degrees. Cos 120. Okay, now cos 120 degree means what? Cos 120 degree means minus 1 by 2. Okay, cos 120 degree is minus 1 by 2. So A square plus A square plus 2 A square into minus 1 by 2. Okay, so 2 and 2 gets cancelled. A square plus A square minus A square. So answer is A. So amplitude of this is A. But if suppose now I ask you what is the phase of the resultant wave? Okay, because two waves being added. So at that particle there will be some changes. So that particle's phase is what? How to find it? Same with parallelogram law only. So what is basically meaning if you go to parallelogram law? What is the phase? Phase means is this angle we are asking now. This theta. Okay. So what is this theta? Say tan theta equal to A2 sin phi by A1 plus A2 cos phi. Okay. Now in this question if I make, okay, so this is A1, this is A2, and this is angle 2 pi by 3. Okay, put it in this one. So A2 value is also A. This is sine 120 degrees by A plus A cos 120 degrees. So A here, this is root 3 by 2. Okay, and this is A plus A into minus 1 by 2. That is minus A by 2. So what will come? Root 3A by 2 by A by 2. Okay, so that's equal to root 3. The tan theta equal to root 3 means theta is 60 degrees. But where were we not knowing it? We were knowing because A1 is also A and A2 is also A. So resultant will be exactly in the middle. And this is 120 degrees. So definitely this is 60 degrees. You are knowing it, and that is proved also. So this formula you already know in vectors, okay, parallelogram law. So same we have to use in this. Consider them as vector and consider this as phase difference as the angle between two vectors and solve it. So we will be getting amplitude also and phase of the resultant wave also. Okay. Alright, see one more. Y1 equal to 3 sine 200x minus 5t, and this is 4 cos 200x minus 5t. So what is the phase difference between these two? Phase difference between these two is 90 degrees. Why? Because this is sine function and this is cos function. So phase difference is 90 degrees. So what is its answer? What will be amplitude? We know 5. Why? Because this is 4 and this is 3. Okay. So amplitude is going to be root over 3 square plus 4 square. That's all. Okay. So answer is 5. That is only he is asking. So okay, no problem. But if suppose angle also is asking, that also we can find. We know that. Okay. Then reflection and refraction of a wave. Okay. So we have to study. Okay, one more. Okay, so what you will do is, for reflection and refraction, we know that this has to be through fixed end. Okay, this is fixed end and this is free end. Okay, we are seeing it on string. So when we are going to make string here, okay, and let's assume the pulse is like this here. This is the pulse. And this is fixed end. This pulse is going like this. Okay, so what happens now? This pulse will be reflected back. Because nothing can go here, refraction is not possible. This side, this is fixed. Okay, so refraction is not at all possible. We are not studying refraction at the moment. We are talking about reflection only. So this is going to be reflected back. And how it will be reflected back? It will be reflected back like this. Okay, and direction of motion is also like this. So in this one, the pulse was going above. Okay, but here it is down. So how much is phase difference between the two? 180 degrees. Okay, upside down it has turned. So in this one, phase difference between incident and reflected wave. Between incident and reflected wave. Reflected wave is 180 degrees. Remaining nothing has changed because this side no energy is going. So whatever energy was incident, same energy is going back. So amplitude is not changed in this one. Okay. So if amplitude is A over here, here also A. So if I write incident wave equation, suppose it is y equal to A sine omega t minus kx. Let's assume it's like this. So then reflected wave equation will be what? Amplitude is same A sine, okay, omega t plus kx. Why omega t plus kx? Because it's going along negative x-axis. So x became negative. So I am writing it as omega t plus kx. But at the same time, you see, here it was above and here it is below. So here amplitude is positive, here amplitude is negative. So it's like this. So yr is minus a sine omega t plus kx. Okay. Now let's see at free end what is happening. Okay. So at free end is like this. Okay. So free end means here is one ring. It's like this. It's reaching in this way. Then next when it is reflected, then it's reflected in the same way. Same way means like this only. Here is moving in this way, here is going back. Any phase change is there? No. There is no change in phase. Any change in amplitude? No. Then what has changed? Only direction of wave has changed. So if incident wave, if we write A sine omega t minus kx, then reflected wave you should write as A sine omega t plus kx. Because direction is minus x, so here minus x will write, it will become plus kx. So this is how reflection through free end we write, and this is how reflection through fixed end we write. Okay, here phase change there, here phase change is there, and it changes by 180 degrees. Here there is no phase change. Okay, so this is reflection at the moment, only reflection. Okay. All right. What this is? Okay. Find equation of reflected wave through rigid boundary and through free end, both. Okay. So we can do that easily. We studied it. Y equal to 2 sine 100x minus 2t, kx minus omega t form. Okay. So through rigid boundary, what we can do? Okay, rigid boundary. Solution is here. So y equal to reflected one. Okay, 2 sine, right, 100x plus 2t. I change its direction. Okay, I change its direction. And at the same time, we know that there will be phase change of 180 degrees, so minus 2. Okay, so minus 2. I hope everything is clear. yr is equal to minus 2 sine 100x plus 2t. That's all, nothing else. Free end reflection. So free end reflection, only direction changes, amplitude remains same. So 2 sine 100x plus 2t. Okay, because it's going to move along negative x-axis. This is along positive x-axis. This is along negative x-axis. Alright? Clear? Okay, so here phase changes by 180, so it's upside down. It is at the moment up, so it will be down. Here it is up for the free end, it remains up. Only direction has changed. Okay, let's see further. Amplitude. Okay, amplitude we'll come back. First we'll talk about refraction or transmission. So in transmission what happens? Where transmission happens actually? Okay, we'll see that in the next one only. Okay, transmission of wave. Transmission or refraction. Transmission or refraction. Okay, so transmission happens when a wave moves from one medium to another medium, right? So there also two possibilities are there, where the other medium is denser medium or other medium is rarer medium. Okay, that we have to see. So how to show you? In a string only I am showing at the moment. Okay, so this is medium 1 and this is medium 2. Okay, and this is, we are saying, is a denser medium. Correct. First one we are making like this. So if suppose one pulse is coming, there is a pulse like this. This is incident pulse. Okay, and this is the junction here, and this is denser. So what happens? Denser one junction, okay, acts like a fixed end. So what happened through fixed end? Phase change of 180 degree for reflected one. So reflected one will come like this, in this way, okay, and transmitted one will be going in the same way here. Transmitted one and incident one, there is no phase change, where incident and reflected one, there is a phase change. This is reflected. And this is transmitted. Okay, from what? From when it's moving from rarer to denser medium. Okay, now opposite of that. It's moving from denser to rarer medium then. Okay, this is denser and this is rarer. Okay, then this is your rather incident wave. It's coming like this. This is junction. So this junction here acts like a free end. Free end means reflected wave also have no change in phase. The reflected one is also going in this way and transmitted one also. Okay, this is reflected one, this is transmitted. Okay, for transmitted one, in both the cases there is no phase difference. Okay, same phase difference, or rather same phase as the incident one. Here also same, here also same. But reflected wave, there is a phase change of 180 degree if you are moving from rarer to denser medium. But if you are moving from denser to rarer, no change in phase. Okay. Now let's go back to amplitude. There is a formula for amplitude where it is here. Here it is. So amplitude of reflected and transmitted wave. This is the amplitude of reflected wave, this is the amplitude of transmitted wave. But there are velocities also. Velocities are what? Velocity, how? It depends on what? Omega by k is velocity. So, okay. So, if change in medium is happening, what is changing? Omega, k or both? Only k. Omega means frequency, okay, does not change with change in medium. With change in medium. Okay. So, velocity of incident wave, Vi, which we are writing as V1 here. Okay, that is, let's say, omega by k1. And velocity of transmitted one, or V2 we'll write, okay. V incident, V transmitted, which is V2. That is omega by k2. And what about velocity of reflected one? That will be same as V1 only. Okay, so incident one, speed is omega by k1, reflected one is also omega by k1 because it's going in the same medium. Omega is same, whereas transmitted one, V2, which is omega by k2. So amplitude of reflected one is V2 minus V1 by V1 plus V2 into AI. That is amplitude of incident wave. AT is 2V2 by V1 plus V2 into AI. AI is again amplitude of incident one. Okay, so this formula, if you can remember better. I have not seen any questions on that directly, so though, but if you can remember, better for us. Okay, then now we have standing waves. Standing waves means interference or superposition of two waves which are coming from different sides, you can say. Okay, so something like this we can have. One wave is here like this. Okay, it's coming in this way. And another one. Another one is coming. Oh. Another one is coming from the other end, like this. Correct. So they are going to superpose one over the other. Okay. So at the moment you can see that this and this, their amplitudes are going to be A1 minus A2. If their amplitudes are same, they are going to cancel each other. But after some time, they will be in same phase also. Okay. So sometimes they are in same phase, be like this also and this also. Sometimes they will be out of phase. Okay. So when they are going to superpose, we are going to get standing wave. And what will be standing wave like? Standing wave will be like this. Like this. Okay. So when these two are, they are in same phase, then what happens? The amplitude becomes 2A. If this is A and this is A, and this becomes 2A here, and this is also 2A. But when this is there, then how is the standing wave? It will be like this. Nothing is there. After this, what will happen? Both will be below. Both will be below means something like this, we can say. Something like this. This is one, and this is the second one. So in that case, what will be standing wave like? In this case, standing wave will be like this. And here again, amplitude is what? 2A. Here again, 2A. Okay, so with time, superposition also, shape of our standing wave is also changing. So what we can say here, what is standing wave actually? Standing wave is also superposition of wave. Oh, it should not go anywhere. Here only I should write. Okay, the superposition of two similar waves. Two similar waves traveling in opposite direction. So can we say that it is actually superposition of incident wave and its reflected wave? Yes, we can say that. Standing wave is actually sum of incident wave plus its reflected wave. It will give us standing wave only. Okay, and how that will be? We can see that. Okay, so we can see that over here. Okay, I'll show you. Right, so see, this is standing wave. Okay, right. So we can frame over here standing wave. Two waves are there. You can see that one is with orange, one is with the blue. Okay, and this is the standing wave is forming. These two are traveling waves, and this green one is the standing wave. These 2 points are here, which are having same position. Same position means what we have shown over here. See. Okay, now these two are waves. Okay, so this point you see here, this point. So this point will be at rest always. Okay, same way this point here. This point is at rest always. Same way this point here. This point is at rest always. Right? Whereas this one, this keeps on moving. Like this. Okay, here also same way, this is at rest, this is at rest, this is at rest. So these are called what? These points are called as node, which always remains at rest. They are not at all moving. And the particle which has maximum displacement, we call them as antinodes. This is antinode. Let's see. Okay, so in this one, these are nodes here. This is node and this is node, whereas this is antinode here. Okay, so this point is only having maximum amplitude. Remaining points amplitude is a lot less than this. Like this one, you see that it's moving from here to here only. This is its maximum amplitude. Okay, from here to here. That's it. Here it stopped. Okay, same way some other particle you take. So every particle in this one is having different amplitude in a standing wave. But entire energy is within this loop only. We can increase its frequency, you can see that more loops we can make. See, there are 2 loops now. But this point here is always at rest. Okay, so this is node. So what is happening because of that? This energy is not going to this loop. Okay, still I have to increase the frequency because closed loop is not there. Okay, I think now it's closed. Yes. Okay, so this is node, and that is node. Right. So energy of this is not reaching energy over here. That's why it's called standing wave. And this orange and blue are traveling waves, which are superposing and making this standing wave here. Okay. So this is the standing wave. You can see over here, if suppose that this one you want to start with antinode, this is at node I have made, starting with node. Okay, right? You can start with antinode also, but that we will be saying when this is free end. Okay, that you will see. But at the moment you concentrate on node only. So this point is node, this point is node, and the energy is within this. This is standing wave. Okay, so that was standing wave. If you are going to add it, equation we will see tomorrow. Okay, we'll start with the standing wave only in tomorrow's class. Today's class we are finishing. Tomorrow we will finish waves and sound. So 11th portion fully will be over tomorrow. Okay, tomorrow is 11th of April, right? So 11th portion will be over and day after tomorrow we are starting 12th. Okay, students? All right. Scan it. Okay, done that?
Yes, sir.
Okay, students, then see you tomorrow. Bye bye.